Dear students, in this video we will discuss four theorems. First theorem is, if an is a sequence such that an is non-zero for any n, that means all the terms are non-zero of the sequence, and ratio an plus 1 divided by an is tending to L. This ratio is tending to L. That means if a sequence is given to you whose all the terms are non-zero, then you can easily formulate a new sequence, an plus 1 divided by an. Then this new sequence is tending to L, where L, magnitude of L is less than 1. Then you have to prove that an is tending to 0. Fine. So this is the statement of the theorem. So now we will prove this theorem. So since this is already given to you that an plus 1 divided by n, this sequence is tending to L, then by the definition of convergence, for a given choice of epsilon, there exists a positive integer m such that an plus 1 divided by n minus L is less than epsilon for all n greater than equals to m. Fine. Now let us take this magnitude of n plus 1 divided by an. Now add and subtract L. So this can be rewritten as magnitude of an plus L minus an minus L plus L. So added and subtracted L. Now applying triangular inequality. So we get less than equal to magnitude of this an plus 1 divided by an minus L plus magnitude of L. Fine. But this is less than epsilon. So this is epsilon plus magnitude of L. Suppose this is equals to k, any constant k. So this is valid for all n is greater than equals to m. Fine. So an plus 1 divided by an is less than k for all n greater than equals to m. This is the conclusion from the above analysis. Now here we will substitute n is equals to m, because this inequality is valid for all n greater than equals to m. So now the minimum value of n will be m. So start with m. So put n is equal to m plus 1, m plus 2 up to n minus 1 successively, and then taking the product of these n minus of equalities, because these are total n minus m inequalities numbers. So corresponding inequalities will be n minus m. So just take the product. So what we get? We get first term, put here n is equal to m. So we get am plus 1 into divided by am into put n is equal to m plus 1. So we get am plus 2 divided by am plus 1 and so on. And last term is n minus 1. So put here n is equal to n minus 1. So we get an divided by an minus 1 is less than equal to, right hand side will be constant. So for n is equal to m we get k, for n is equal to m plus 1 again we get k, and so on, total n minus m times. So after resolving this, you can see that this term is cancelled out with am plus 1, am plus 2 will be cancelled out with am plus 2 and so on. So the only left term will be an and am. So that's why, and in the right hand side we are having k raised to the power n minus m. So finally we have this an by am less than k raised to the power n minus m. So now you can take this am in the right hand side. So we get magnitude of an less than k raised to the power n, this magnitude of am, and this k raised to the power minus m can be bring in the denominator. So k raised to the power m. Now here m is actually a fixed number. So obviously am will be a constant, k raised to the power m will be a constant. So this is a constant term. Fine. Also what is our epsilon? Our k is this. If you remember, what is your k? K is epsilon plus magnitude of L. So here what is k? K is epsilon plus magnitude of L, and magnitude of L is already given to you less than 1. Then obviously your k will be in between 0 and 1, because this quantity is less than 1, and obviously this is a positive quantity, so greater than 0. But epsilon we know that is greater than 0, so their sum will be again and greater than 0 and very small quantity. That's why k will be in between 0 and 1. Now if k is in between 0 and 1, so k raised to the power n tending to 0 as n tending to infinite, and that's why we can say that this term tends to 0 due to this factor k raised to the power n as n tending to infinite. So magnitude of an tends to 0 as n tending to infinite, and that's why limit of n tending to infinite an will be 0. So this is the theorem. So this is the proof of the theorem. Now the second theorem, important theorem, Cauchy first theorem on limit. Fine. This is regarding the arithmetic mean. What is the statement says? If limit n tending to infinite an is L, then limit n tending to infinite a1 plus a2 plus an divided by n is also L. That means the arithmetic mean of initial n term is again a sequence and then tending to infinite, so we get L. So we have to prove this. To prove this, we have to construct a sequence with the help of an, and sequence is bn is equals to an minus L. Now find the limit. Limit n tending to infinite bn is equals to limit n tending to infinite an minus L, because this is a constant, but this is already given to you L, so L minus L is 0. Fine. So now from first equation, an is nothing but bn plus L. So this is an is equal to bn plus L. So since an is equal to bn plus 1, then if you, this is an is equals to bn plus L. So what will be a1? a1 will be b1 plus L, a2 b2 plus L, and so on. An is equals to bn plus L. Now take the sum of these two. What you will get? You will get a1 plus a2 plus an is equals to b1 plus b2 plus bn plus nl. Now divide by n. So a1 plus a2 plus an divided by n is b1 plus bn divided by n plus L. This is written here. This is 2 star. Fine. Now we will show that limit of n tending to infinite, because what is our target? Our target is to show this. That means our target is to show this quantity as L. So that means this quantity should be L as n tending to infinite. And this is only possible because here is also L. So this quantity should be L only if this quantity should tend to 0. If this quantity tends to 0, then we can say that this quantity tends to L. So it is enough to prove that limit n tending to infinite b1 plus b2 bn divided by n is 0. If so, then we can easily prove our proof. Fine. Now what we have from equation number 2, limit of bn is already 0. That means for a given epsilon, there exists a positive integer m such that magnitude of bn minus 0 is less than some epsilon by 2 for all n is greater than equals to m. Here we have selected epsilon by 2. Fine. So now this is nothing but magnitude of bn is less than epsilon by 2 for all n greater than equals to m. This is equation number 3. Also, if this limit bn tend to equal to 0 from here, question number 2, that means sequence converges, and if sequence converges, so obviously sequence is bounded, and if bounded, so there exists a positive number k greater than 0 such that magnitude of bn is less than k for all n. Here is for all n. However, here is for all n is greater than equal to m. Fine. Now we will use these two conditions to prove this. So now here we will start with this, because we want to prove that b1 b2 bn limit is nothing but 0. So take this magnitude b1 b2 bn by n minus 0. 0 is the limit, which is equals to this magnitude of b1 plus b2 bn by n is equals to, n is a positive number, so you can take it outside. So 1 by n magnitude of this. Now apply the triangle inequality, but before that 1 by n you can expand this b1 b2 b3. Somewhere is bm plus bm plus 1 and last term is bn. Now apply the triangle inequality. So 1 by n magnitude of b1 plus magnitude of b2 plus magnitude of bm plus magnitude of bm plus 1 plus magnitude of bm plus 2 and last term is magnitude of bn. Why we have bifurcated it? Because we are having these two conditions. This is the reason. This equation holds for all n greater than equals to n. However, this condition holds for all n belongs to n. Fine. So now, if you will see here, there are two parts. One is from B1 to Bm, another one is from Bm plus 1 to Bn. For this part, we will use equation number 4. This equation we will use because this is valid for all n. However, for the second part, we will use the definition from equation number 3. Fine. So here we will replace all these quantity by epsilon by 2 using equation number 3, and here all the terms are replaced by less than k using equation number 4. So these are total m quantities, so that's why their sum will be km, plus these are total n minus m quantities, so n minus m into epsilon by 2. So assemble all these, so km by n plus n minus m divided by n epsilon by 2. So this is km by n plus this quantity is obviously, because n minus m by n is nothing but 1 minus m by n, which is obviously less than 1. So this quantity can be written as plus epsilon by 2. This can be replaced by less than 1. Fine. So now km by n can be considered as epsilon by 2. This is only possible if n by km is greater than 2 by epsilon. Just take the reciprocal of this. From here you can find out n. So now this quantity is any real number, any positive real number, any positive real number. For example, say 2.5. Then you have to take any positive natural number which is greater than this number. So you have to select m as any number which is minimum number is obviously 3. If this quantity is, for example, say 2.5, then this positive number p will be 3. Fine, this is just an example. So that's why for this choice of this is nothing but this km by n is less than epsilon by 2. So now we are having how many numbers? We are having this number p, a natural number, and this m. So take, and we want to combine these two. So we have an option with the help of maximum. So q is equals to maximum of pm. Fine. So now substitute all these values in equation number 5. So b1 plus b2 plus b2 and by is less than epsilon by 2 plus epsilon by 2, because here this is our assumption. And now this number is greater than this number q. So that's why this magnitude is less than epsilon for all n greater than equals to q. That's why limit of this b1 plus b2 bn by n is 0, and hence from equation number 2 star, this a1 plus a2 plus an divided by n is L. This is the proof of the theorem. Now converse of the theorem is need not be true. That means suppose this sequence is there, is arithmetic mean converges. Here in this equation the sequence an converges to some number L, then the arithmetic mean is also converges to L. But converse need not be true. That means if arithmetic mean this converges to L, then sequence need not be a convergent sequence. Here is the proof. Here is an example. So consider this example. This is not a convergent sequence, obviously. This is an oscillatory sequence, finitely oscillatory rather than. Take the arithmetic mean. Now depending upon the number of terms, suppose you are adding initial 3 terms, then what will be the sum? Sum will be minus 1. If you are adding initial 4 term, then sum will be 0. So depending upon number of terms, if number of terms is odd, then the sum will be minus 1 by n, because you are taking the arithmetic mean. And if number of terms are even, then the sum will be 0. Fine. Now if we take n tending to infinite, so when you take n tending to infinite here, then you are getting 0, and then here if you are taking n tending to, again you are 0. So ultimately this limit is nothing but 0. Either from here or here you are getting the same answer, so 0. But limit of n tending to infinite an is non-zero, because this is an oscillatory sequence, not a convergent sequence. So this will not converge to 0. So converse need not be true. So the next two theorems we will prove in the next video. Thank you.